who have published papers in A venues, international A venues, and we invite them to come here and present their talks. And so the research track and also the AVS track, we were asked to nominate, present to pick papers from, so we looked at, for example, SIGMOD, KDD, CVPR, all of the data management, data science, and AI ML venues. We were looking for the last 2+ years, and then we invited the papers where there were either best paper nominations or that they were notable papers.
The online audience.
Oh, I see. Yes, sorry. Where there were notable papers, and then where also the presenters were mainly in India and then also were able to come and present. We wanted to make sure everybody could be here in person so that everybody could interact with them. And so we have 3 presenters, and what I will ask each of the presenters to do is, when you present your paper, also just tell us a couple of sentences about where this paper has been presented, etc., so that you provide some of the context for maybe new PhD students who may not be as aware of those different outlets. And epic fail, we didn't find a session chair, and I also can't read the screen, bad resolution, so I'm going to invite the 3 speakers to read the titles out and then tell us about what you're going to be presenting. Thank you.
I'll introduce myself. Good afternoon, everyone. My name is Chetan, and I'm a faculty in Computer Science Department at IIT Delhi. And this work that I'm going to present, that was published in CVPR 22. So it's a good conference, top conference in computer vision area, and it happens generally in June. So this was about 6 months old work. All right. So after the introduction, just a brief disclaimer. So I'm not a native to the CODS-COMAD, so I belong to the computer vision community. And just like you have CODS-COMAD, we have ICVGIP. So where we present the visions style of work that happens in December. So it was in IIT Gandhinagar last time. So my area is vision, so where we deal with all kinds of image. So we basically would like to discover some information from the images. So if I have an image, I would like to know if there exists a car in it. If there is a car, where is the car? If we are talking about the videos, what kind of actions are being performed in that? So these are normally the things that we kind of do in vision. So traditionally, we used to work with tools like linear algebra, image processing for making these things work. These days, with deep learning, etc., we also use many machine learning tools for doing this thing. So increasingly, my area now is somewhere between vision and machine learning now. So that's what this paper also is about. I believe that's why the organizers felt that this is appropriate to talk about it in this venue. Okay, so now coming to this specific work. So this will fall broadly under the healthcare domain, where we are talking about the GBC, which is called the gallbladder cancer. And as we will go in the slides, I'll slowly walk you through why we are interested in gallbladder cancer, and so why we are interested in the gallbladder cancer, and why specifically from the ultrasound. I'm sorry, so this just went to the last slide. That's good. All right. So just a brief introduction about our group. Without, other than what I'm going to present today, we do lots of things in vision. So all these things, so healthcare is one aspect that I'll be talking about. But as a vision group, we also work in the mobility space where we are interested in the scene understanding from the cars. We also work on the variable camera where you put the camera on the shirt, for example, and then you try to understand the images and the videos that come out of the variable cameras. We also work on the trustworthy AI. Again, this is a topic which will be very close to the CODS-COMAD theme as such. But in this case, also our interest mainly is in the images. So I'm interested in making the systems or the AI-based systems trustworthy. But we talk specifically when these systems are the image kind. So the image classification, object detection, so those kind of systems trustworthy. So many times the kind of algorithm that often get presented, which let's say will be applicable for data science or the AI, do not directly apply to the vision. So for example, if I'm saying that if there's a bias in the system, in a tabular data, you'll say that, okay, just change that field and just check again. In the vision, if I say that you are you are biased towards the skin color, I just do not have an option to change the color and then try again. So we have to often develop different kinds of algorithm for the trustworthy AI. So we also work on socially relevant problems like assistive vision, etc. Yeah, so this is the brief introduction about our work, and I'll now come quickly to the topic of this talk. So today I will be talking about the gallbladder cancer. So it's the most common biliary tract cancer. Worldwide, there are about 165,000 deaths every year just because of this. And the 5-year survival rate is very abysmal. Okay, and typically after the detection, the mean survival rate for the patient is roughly about the 6 months. The primary reason for this low survival rate or the bleak survival rate is because the metastasis happen pretty quickly in this, because there is a the gallbladder is just adjacent to your liver, and so if there is something wrong with the gallbladder, it quickly goes into the liver and then metastasizes to the other parts of the body. And so because the role of the gallbladder is just in the digestion process in that, so many times whenever you have this cancer, it just goes undetected for a long time until it's too late. So on the other hand, many of us, for one reason or other, keep going through some kind of an ultrasound of the abdomen. So the radiologists do have access to this ultrasound, but often they are not exposed to the gallbladder cancer. So that's where we would like to make an impact. And if there could be an AI-based algorithm which just takes these ultrasound images and can detect whether the patient has a gallbladder cancer or not. So that's the broad agenda. So this is the general picture about the gallbladder cancer, but we, as in the India, are specifically badly disposed against the gallbladder cancer. So we have the second highest incident rate in the gallbladder cancer after Chile. So between Chile and India, we have the highest the incidence of the gallbladder cancer. That makes it even more relevant for us that the groups from within India should work on this kind of problem, where typically the Western population is not predisposed, so they are not really very interested in working on that problem. So the AI plus healthcare is a very it's a very popular domain these days. Many people are working on it. But what we will see is that they are not specifically working on the gallbladder cancer, which is primarily the India plus Chile disease, one can say. So I hope that I have been able to motivate that the gallbladder cancer is something that we should be working on within India. Now, why we should be working specifically from the ultrasound images? Okay, so I would like to remind you why this ultrasound word is important, because many times when you see the healthcare problems, so you will be seeing from the X-rays, the CT scans, the MRIs, things of that sort. And so I'm not sure if you have noticed, but all of these modalities, the imaging modalities, are very controlled. So if you have to take an X-ray, there is a person who will push you against particular wall and then take a chest X-ray, for example. If you are, let's say, doing an MRI, you will be lying down in a very specific posture. The machine will be at a very particular position and then take the images. On the other hand, in contrast to all these modalities, the ultrasound is a modality where there is a sensor, the handheld sensor, and the doctor is going to put it on top of your abdomen. What that means is that one, there is no controlled imaging that happens in the ultrasound. From the machine learning perspective, what you are saying is that the data that is coming is very much varied. I mean, I'm sometimes looking at the abdomen from this angle and sometimes from this angle. And usually in the ultrasound, you actually take a picture of a plane sort of stuff. So you are actually cutting a 3D object in certain planes, and then that's the image that you are getting. And from that image, you have to make sense whether there is a gallbladder cancer present there or not. So the ultrasound, just the fact that it's a handheld scanner and there is no controlled acquisition of the images makes the problem challenging. Yet we would like to do the ultrasound because that's the thing that we do not control as a machine learning researcher. That is something that is given to us. So the ultrasound imaging is something, the modality of the choice for detecting gallbladder cancer. Typically, all the patient for whom let's say the next level of studies will be suggested will have the first diagnosis through the ultrasound. So if we would like to go at the screening stage, we should like to go at the triage stage, we have to really make an impact, or we have to really make inroads through the ultrasound images, even if we understand that detecting, for example, gallbladder cancer from the CT scan may have been a much easier machine learning problem compared to if I'm talking about detecting gallbladder cancer from the ultrasound. So we do want to work with ultrasound. We have our reasons to start with, but because this is not necessarily a Western population disease, so there is not much work using AI ML on the GBC detection. So we are perhaps one of the first groups all over world also who are working in the gallbladder cancer, and we have some results which I will be presenting today. Okay, so now why I would like to do the gallbladder cancer specifically through the AI, because as I mentioned, the radiologists often are not very much exposed to this kind of a disease. It's uncommon for them. The view variation also, they do not often go through that kind of a training in the gallbladder cancer detection. And even if the person is actually have a cancer and you are still, you are scanning in the person also, there are chances that you might miss it. So we hope that if with this kind of an algorithm, we will be able to detect the gallbladder cancer at an early stage, and which will improve the survival rate for the patient. So that's the motivation for doing the AI-based automated detection of the gallbladder cancer. Now, what are the challenges in the gallbladder cancer detection? So as I mentioned, the first thing, which is actually not written here, is the viewpoint variation from the radiologist, because it's a handheld scanner. The other thing is the anatomy. So we are talking about the abdomen, which is like the flexible part of it. So you press the sensor and it changes the shape, things like that. And the gallbladder cancer is just kind of pushed with the liver. So it has a very thin boundary with the liver. In the image, it looks very blurry. And we even detecting where the gallbladder is from the ultrasound images is challenging. I'll be showing some images soon to you. So the anatomy of the liver plus gallbladder is challenging for any AI-based task. So that makes the gallbladder cancer detection also challenging. The USG images adds the additional complexity, because I can perhaps argue that in all the modalities that I talked about, whether it's an X-ray or MRI, CT, the SNR, the signal to noise ratio, is perhaps the worst in the ultrasound. So you might have seen yourself also that when you go through the ultrasound, the doctors will typically put some kind of a gel between the sensor and your skin, because even if there is a slight amount of air, that adds to that noise. Okay, so the ultrasound wave will get attenuated more if there is an air in between. So one has to put really a good pressure with the skin so that the sensor remains attached all through with your skin, and you get the good images. So it's a pretty noisy modality. And then the handheld part of it, so it's being held by the doctor in the hand, so the viewpoint variation. And so since we are the first group and there is not much interest really before us in the GBC, so there's a lack of annotated data, a lack of data set, in fact, not to talk about the annotated data sets. Okay, so this is just to give you some idea about the kind of challenge that we're talking about. So here you see the gallbladder. So this black portion is the gallbladder here. Okay, and so I'm showing 3 images just to get a sense of it. So this is a normal gallbladder. This is a benign gallbladder where there is some abnormality present. So this thing that you are seeing are the stones in the gallbladder. And this is a malignant gallbladder, because we are not able to, so this is liver. And there is a boundary between the gallbladder and the liver here, so which is clearly distinct, which is also apparent here also. On the other hand, in this case, the wall between the liver and the gallbladder has just disappeared. So that's what makes it, so now you can understand from these images, we have to develop a vision-based algorithm, the ML-based algorithm, to really classify one image from the other, one kind of image from the other kind of image. And so the ultrasound sensor is typically here. So you are projecting the sound waves. So they will just go in a sort of an umbrella shape, kind of. And so wherever there is something that the sound waves cannot penetrate, you will see a sort of a shadow here. So once you have, for example, a stone here, so this is the shadow because the ultrasound waves were going from up, so they were stopped here and they cannot go beyond it. So there is nothing that is reflecting for the sensor, so you see that dark shadow stuff here. So this is these are the kind of images from which we have to basically, let's say if I talk about the machine learning problem, we are interested in doing an image classification. So that's a classification problem. I give you an image, you tell me whether it's a normal, benign, or malignant. That's all. Okay, so then there will be, so because we are talking about the ultrasound, so there will be the sensor artifact. So one artifact that I already mentioned is the shadow. So the moment something comes above, everything below is dark. And from the machine learning perspective, many times the algorithms will start seeing this because usually when you have this ultrasound, the dark portion belongs to the gallbladder. Okay, so if you have a shadow, this shadow can start mimicking the characteristics of the gallbladder, and the algorithm will get confused. Where is even the gallbladder? Not to talk about whether it's a malignant or benign. Okay, so for example, there's no gallbladder here, but the classification algorithm will say there is a gallbladder and it's malignant. So the first contribution of this work that we are talking about, the CVPR 22 work, is that we propose that there should be a data set, and this is the data set that we collected. So we have a collaboration going on with the PGI Chandigarh. So this was the data that was collected there over a certain period from multiple radiologists. So we do have the radiologist kind of variation. So this data set consists of the 1255 samples from 218 patients. So why I choose to mention this number here is that because sometimes in the machine learning community, we are used to looking at the data which is tens of thousands or millions. And when we are talking about the healthcare, the medical imaging, this is perhaps the largest number that you're going to see. So once we have to train the model with such a small number, we have to be very careful that there may not be too many sample variations that are present. So we have to make our model robust in this small data set. So it's still not a few shot recognition problem. So we do have in the vision the few shot recognition where we have only few samples, 5, 10, 15, that kind of stuff. So it's not still a few shot recognition problem. It's still a classification problem. We have 1,000 data, but it's not the kind of data that we are used to in the standard machine learning community. Okay, and to top with that, there will be lots of what we call the intra-class variation, which means that the two normal gallbladder can look very different depending upon which viewpoint that I'm looking at, and the patient variations also. And there can be very small difference between a normal and a malignant. Okay, so we are just looking for this blurred boundary between the gallbladder and the liver. So if that boundary is absent, that's the first indication, the strongest indication of a gallbladder cancer. So overall, from the machine learning perspective, it's a hard problem. Okay, so we are talking about large intra-class variance. We are talking about the low intra-class variance, low inter-class variance. We are talking about the small data sets, and we require a very high sensitivity. You do not want to miss a patient who has a cancer. Okay, you perhaps can adjust still with few false positives here and there. Okay, so this was this is the data set, and now coming for the solution. So we propose a particular kind of an architecture. So from the vision perspective, it's a decent architecture. I do not want to go into the details of the architecture, but just to give a very high level, because we have the large intra-class variance and the small intra-class variance, something that we have to make sure in the upfront is that we do not look at the region which are unimportant. Okay, and whenever we are talking about the gallbladder and the cancer, there is a very specific region that we are looking at. And if I just give an image as such, the whole image of the ultrasound image to access to the model is not going to learn anything. I mean, I just got 1,000 images roughly, and such noise images, things of that sort, and the model will simply just not learn anything. So first thing that we have to do in this case is that we pose the problem as detection/classification problem. Okay, so original problem is classification still. I'm still interested in knowing whether a particular sample is malignant or benign, but I do pose it as a problem of detection. So what do we do in the detection is we are interested in detecting a particular pattern in the image. Okay, so in this case, what we do is we first detect where is the gallbladder. Okay, so because the gallbladder cancer is present only in the gallbladder, so I have to first detect the gallbladder. So that's how we pose the problem. So we first do the detection and then do the classification of that detected region. Okay, so this is the kind of output that one gets. So you will typically get a good region in this. So remember that although we have posed the problem as a detection, the first part of the problem as a detection problem, it's not really what I'm interested in. So a little bit smaller rectangle, a little bit larger rectangle is still okay with me. Okay, I was just interested in taking out this extra region, which is just making my problem unnecessarily harder. Okay, so I just make this detection problem first. So now I have attention region, if you would like to talk in terms of the transformer. So I have this attention, but I have an attention which is hard-coded in a certain sense, that I know which region I need to attend to. And then we have to do a second order pooling. Okay, the MS stands for the multi-scale and SOP stands for the second order pooling. So both of these things are necessary. Multi-scale is necessary because the size variation are a lot in the gallbladder cancer. So we have to look at the image at a multiple scale. And the second order pooling is often necessary because the first order relationship that typically a network will get are not sufficient for the classification. We are often talking about the texture kind of a feature. So the correlation and the other second order pooling feature often works better. So this is SOP is not really our stuff. The people in the vision have shown that the SOP works better for the texture. We just took it for the gallbladder cancer. We just identified that our problem also falls under the texture classification, and we just pulled this SOP architecture in ours. Okay, so this is what we're talking about. So for example, so these are the regions and the classification that we are able to manage with our model. One more thing which I wanted to mention here. So as I told you, that one is that this is really a texture detection problem. Now this texture is often getting altered because of the sensor noise. Okay, so there is so when the sensor is taking this noise, the sound wave gets reflected from random places also in the region, which means that I will get this what in the vision we call the salt and pepper kind of a noise. So this random pixel will just start becoming black and white. However, I mean, the humans usually are able to normalize against it, that we are able to see that this is the random texture, and we are able to focus correctly on that there is a boundary or not. But this is not so for the machine learning model. And even when we developed this model, we were still getting this bias from this random texture. So I just add a little bit more noise, a little less noise, and the model starts to go awry. So what we what we did for that case is we took some ideas from the visual acuity. So this is something that we talked that this is a work that has been done at the MIT for the understanding of the human vision. And they came up with a very nice model of the human vision. So what happens is that when a child is born, so the child is born with a very bad eyesight. So whatever he or she is seeing is a very blurred image. And from, let's say, the 0 months to 12 months, the vision actually slowly improves over a period of time. Okay, and at the same time, the vision system, the brain, which is interpreting these images, is also getting developed. So the key insight from the machine learning perspective is that when, I mean, if you imagine this, the brain as the biological or the artificial model of the ML, so this brain sees the images which are blurred first, and then slowly the resolution changes. And which means that we look at the images in a certain style, blurred to high res. Okay, and that gives us invariance, that gives our brain, our understanding, a certain invariance against some kind of a noise. So that's what we wanted to also take inspiration from this blurred to the high resolution, and that's what we did also in our case. So we deliberately started with the images which were blurred. So the initial epochs, all the images of the gallbladder cancer that is being fed to the network are all blurred. And then over the epochs, we slowly change the resolution or slowly reduce the blur that we were introducing in the images. Remember, it's not a blurring augmentation. So many times in the vision, we do blurring augmentation also. But that blurring augmentation survives all through the epoch, and that's random. So some images you will do blur, some images you will do flip, things of that sort. This is a very targeted blurring. Okay, so I blur all the images in the beginning. I will reduce the blurring in the second epoch. I'll further reduce the blurring in the third block. And perhaps by the time that I come to the 10th epoch, I will just make the blurring 0 and let the model train 5 epochs for the resolution. Now, what it gives is that the moment I have the blurring, there are this noise that I was talking about has gone, but the structure has also disappeared a little bit. This noise has this blurring has worked both ways, but it allows the model to look at the broader shape because the details are now missing for the model. So the initial epochs model start to learn the shape, and in the later epoch, when I'm giving the higher resolution, it starts to learn the higher resolution, these boundaries between the liver and the in the gallbladder, because these are the high resolution images now. So this is what we refer to as the curriculum. So visual acuity based curriculum. So there is a certain motivation why we are doing this specific stuff. Okay, we see that if we use this kind of a curriculum, the false positive rates drop and the model learns a more robust representation of all the things. So these are some of the key results. So now just put this all together. So we have a certain data set. We do this attention-based stuff in the first pass because we would like to focus only on the gallbladder. In the second pass, we do this multi-scale second-order pooling kind of an architecture. And in the third case, we just say that we will do the visual acuity-based curriculum learning. So put all these three things together, and that's the architecture, that's the model that we have proposed. And these are the key results that come out of it. So these are all the state-of-the-art alternatives that we have got. So you will see that the GBC net as such works with the 87%. If I add the visual acuity, there's a 4% jump in the accuracy. And in terms of the sensitivity, specificity, all the places we get much bump up. So for example, 92.9 to 97, that's the kind of accuracy that we see. The important thing that we notice is that this accuracy, at least in the limited data set, is actually better than the radiologists. Okay, so if I actually show the same images to the radiologist also, there is a significant difference actually in the accuracy. So even with this 1,000 images. Now I do not want to oversell what we have done in the sense that I do not say that, okay, go tomorrow and just start putting this algorithm into the clinics. And so this is still in the limited setting. We have to do the multi-center study. We have to look at the more patient. We have to see how the generalization performance is. But this is a good start. It looks like that there is a certain thing, that there is a certain milestone that we have been able to achieve, and we have now need to go to the multi-center study. These are, let's say, some of the qualitative results. So this is the kind of region that it identifies, this the red regions, and then classifies on the basis of that. Thank you. And so all the code and the model that we have are available on our website, and this is the QR code which will just take you directly to the website. Thank you. Any questions?
So you compare with the radiologist, so ground rules would be what panel of radiologists?
So all these images have the corresponding biopsy also available, so that's the gold value for us. Yes. So we have the license agreement as part of the stuff. So you have to give us and send us form signed that you will use only for the research. And I'm from IIT Delhi. IIT Delhi. Right. Yeah, you just search my name on the Google. Hopefully, you will land up on my page. The source code of the model. Yes. I don't think that we have a very nice GUI tool that we can just do it. Yeah, but the model is available. Chetan, Arora, IIT Delhi. Computer Science Department. Computer Science.
Any more questions?
So in the earlier part of the presentation, you mentioned you showed an image wherein the stones were sort of blocking the rays. So I was wondering, when you're detecting and sort of using the smaller rectangle for classification, aren't you losing that information?
I'm sorry. How am I using?
So
I'm just going to the picture, but you asked your question.
Yeah. So showed when there are stones, it kind of blocks the. Yeah. So that is in some sense some information, right? So is it of any value? Which is outside the rectangle you're detecting?
So typically, the gallbladder has this bile juice which makes it black. So anything which is whitish is not native to the gallbladder. So whitish things are stone that I know even without this shadow, actually.
Got it.
I think the question was whether it's useful information or you just ignore it.
at the moment, the shadows may not be as useful as this.
So some bit of shadow will come because I'm doing a bounding box. So
Okay.
some bit of shadow will come, but what I'm saying is that if I were to say that whether there are stones present in the gallbladder cancer or not, that I will be able to classify even without looking at the shadow. So that part.
So I think in the interest of time, I'm sorry, but we have to move on. But I think the speakers will be available.
Yeah, I can talk to you after the session.
So our next speaker is Rajdeep Mukherjee, and I'm going to let him set up his presentation. I'll just mention that Rajdeep is finishing up his PhD, I think, and he has received a number of Best Paper awards. We picked the one from Web Science and Data Mining for him to present here.
Hello. Okay. I hope I'm audible. Okay. So hello and good afternoon, everyone. I am Rajdeep Mukherjee. I am a final year PhD scholar at the Department of Computer Science and Engineering from IIT Kharagpur. I primarily work with Professor Nilay Ganguly and Professor Pawan Goyal, and I'm also part of the Synergy Group, Complex Networks Research Group at IIT Kharagpur. So today I will be presenting this paper titled MTLTS, a multitask framework to obtain trustworthy summaries from crisis-related microblogs. So this paper was accepted at Wisdom 2022 last year. It is one of the top data science and data management conferences in the world. So yeah, I really thank the organizers for selecting this paper and giving me this opportunity to speak in front of you. Okay, so to give an overview of what we are trying to do here, certain adversities, such as any natural or man-made disasters, whenever these things happen, they escalate the speed of news sharing, maybe message sharing, maybe tweet sharing over social media platforms. But the tweets or messages, maybe Facebook messages or tweets posted during such emergencies, they usually contain a lot of important information. It may range from crisis, critical situational updates, details about the victims who are getting affected at on the ground, then whether there are any requests for aids, and finally the general public sentiments, because this is very important for many people. Like the politicians also need to understand like where the situation is going on and how much actively we need to take care of the situation, and we need to deploy the services over there. But I mean, going through this huge amount of tweets is definitely not possible for any humanitarian organizations who are trying to provide help out there. So there is definitely a need to summarize this information so as to enable several concerned stakeholders to take action. It may be humanitarian organizations, crisis responders, and in general the general public. But disaster summarization or summarization of disaster-related data or crisis-related data, this is not a new problem. So why do we have to come up with another new solution? So this has been pretty widely researched over the literature. So where do those existing summarizers fail? So for this, let us take the example of this unfortunate incident, this Charlie Hebdo shooting, which happened in January 2015 in Paris. So I would just read this piece of text here. So on January 7, 2015 at about 11:30 a.m., two French Muslim brothers, Said and Sherif Kouachi, forced their way into the offices of the French satirical weekly newspaper Charlie Hebdo in Paris. And armed with rifles and other weapons, they killed 12 people and injured 11 others. So this is the actual fact that happened over there. I have not taken the entire transcript from Wikipedia, the source is there. But there are a lot of details which got published later on. Like what is the true fact about this incident? Now, let us look at this system-generated summary. So this summary has been generated by one of the state-of-the-art disaster summarizers. So Just by taking a look at this summary, do you think that there is any error? Like we see that all the sentences are like properly well-formed sentences, and they are giving proper information about what actually happened. So we generally, I mean, just by looking at the summary, probably we won't be able to understand like what is going on wrong. But the problem is that there are several rumors or misinformation in this. Both the first sentence as well as the second sentence, both are rumors or misinformation. Okay, these are not actually the true statements, because the first one is definitely a rumor. It did not happen at Eiffel Tower. And the second is misinformation because total 5 cartoonists were killed, whereas the tweet says that 4 cartoonists were killed. Only the last one is correct. It's not just because it has a link, but there are other dimensions to it, which we will come across later. So why does this happen? So first of all, there is this lack of social media moderation. Like anyone and everyone can tweet whatever they want. So many people can deliberately, try to misguide you by posting something which has not happened. So basically, it's a deliberate rumor, deliberate piece of misinformation which is being propagated maliciously. So that is one reason. And the second reason is that when the incidents happen at the time of unfolding of the event, many a times, authentic information from authentic or reliable sources are not present. So many a times, the misinformation which gets propagated, that is not deliberate, but it just happens because of this particular case. So the thing is that in standard summarization tasks, how we evaluate the summaries is basically using standard Rouge-based metrics, which basically tries to evaluate your system-generated summary against some ground truth summary with respect to span similarity-based metrics. But the thing is that we need to look beyond Rouge, or we need to look beyond metrics which are very similar to Rouge, because in this case, the trustworthiness of the summaries also needs to be evaluated. Because even if a summary which is being generated by your system, even if it is content rich, but if it is not making the proper claims, or is providing you the proper details which actually happened, then there is no use of the summaries. This cannot be used by anyone. So trustworthiness needs to be evaluated in this particular domain. That's what we motivate. Okay, so what is the solution? So we basically motivate the task of trustworthy summarization, and given a bunch of tweets which have been posted around a particular event, like this is the final output of our system. What we do is that we create a summary, and against each of the sentence which has been picked in the summary, we also give a score. And the score is basically the joint score representing the verifiability and the summary worthiness of the tweet. So both the things have to be jointly optimized in our system, and that we will look later. So these are some prior methods which already have made their way into the literature. But the problem with all these methods is that they do not consider the credibility of the tweets. They only consider the summary, the tweet content, the semantic content of the tweet, because of which the summaries that they generate, more often than not, they are not trustworthy enough. The only proper baseline for this particular task is Verisum, which came out in CIKM 2019, if I'm not wrong. Yeah, CIKM 2019. But this takes a pipeline approach. So this is very intuitive. So first you decide whether a particular tweet is credible enough, it is giving you the proper information or not, and then you decide whether it can be included in the summary. It's a very intuitive thing, but the problem is that any pipeline approach will definitely suffer from error propagation between the stages. So what we want to do is, first we want to design an end-to-end system in order to generate a content-rich and trustworthy summary from large volumes of crisis-related tweets, which are posted during such unfortunate incidents. And secondly, different from existing disaster-specific summarizers. When I'm mainly talking about the summarization problem, then the existing disaster-specific summarizers, they mainly work by optimizing certain keywords which are very much, the presence of certain keywords which are very specific to those events, and all of these are unsupervised, by the way. We want to take a supervised approach for our model. And finally, we also wanted to address the gap between vast body of literature on general document summarization versus comparatively limited research on social media summarization. So this is our proposed approach. I will come to the diagram later in a couple of slides. So our main objective is definitely to summarize the collection of tweets posted during such events. So tweet summarization becomes our main task, obviously. But tweet credibility verification is a very important auxiliary task that we take, okay, that we consider. So our proposed model, MTLTS, is basically trained using a hierarchical multitask approach that implicitly mimics a pipeline approach. So first, implicitly mimics a pipeline approach, but it tries to address the limitations of a pipeline approach. So how we do this? So we train the verifier. We have two modules, the verifier module and the summarizer module. So the verifier module is basically trying to verify the credibility or the veracity of the tweet that it is reading. And then the summarizer module will try to collect all these tweets and then decide upon their summary membership. So we train the verifier at a lower layer. So intuitively, it is mimicking a pipeline. So verifier is being trained at a lower layer, and its predictions are being used by the summarizer, which is being trained at an upper layer. So I would just take one more slide before I jump to the the model diagram. So formally, let this T represent a data set of tweet threads. Why tweet thread? Because every tweet comes with a source claim and then all the replies along with it. Okay, so it becomes a propagation tree-like structure. So we call this entire thing a thread. So let's T represent a data set of tweet threads posted during a crisis event, where it is headed, every thread is headed, it's a tree-like structure which is headed by the source tweet or the claim, whose veracity or the credibility needs to be determined. Okay, and the reply tweets RI star are direct or indirect responses. It may be replies, it may be forwarding the same tweet again. So these are represented by RI star. Okay, and our multitask objective is formulated as a supervised problem, supervised classification problem, which learns a classifier F. Yeah, so basically, which learns a classifier F from labeled source tweets, where SI is basically depending upon whether it is verified SI is a collection of the verification probability and the summarization probability of the source tweet SI, and veri can be one of the two things, either verified or unverified. So these are basically the labels. These are self-explanatory. So yeah, over to the model diagram. So here you can see that there are two modules. On the left, we are showing the verifier module. On the right, this is the the summarization module. So how it is being trained? So I will first discuss about the summarization module. So this is built on top of SummaRunner. So SummaRunner is a state-of-the-art, not state-of-the-art, but it is one of the seminal extractive models, extractive summarization models. So it mainly consists of two layers. So in the first layer, given a particular sentence, in the first layer, the word representations are learned, and in the second layer, and the sentence level representations are learned. After that, on every particular sentence, a decision is taken whether to include that sentence in the summary or not. So we basically replace the first layer by BERT tweet. So BERT tweet is a BERT model which is pre-trained on a large collection of tweets. Because we are working with tweets, so we found it to serve better our case. So fair enough. So and on the verifier side, so this is based on Cascade LSTM, which is again a state-of-the-art rumor classification system. So what Cascade LSTM does is that every green circle that you see over here, that represents a tree LSTM node, and the head of this particular tree is basically the source tweet, for which we have to determine the credibility, and all the remaining are basically the replies. Okay. Now, in a Cascade LSTM, what happens is that so every green circle here is a tree LSTM node. Okay, and in Cascade LSTM there are two directions in which the information is flowing. Okay, the dashed lines basically show you the information flow from the source to the replies tweets, and the solid lines basically represent the other way around. Okay, from the reply to the source. So basically, when this entire model is trained, then the information across the entire cascade is taken into consideration, and not just one of the directions. So that is the beauty of Cascade LSTM over tree LSTM, which was a previously proposed approach. Okay. So now in this Cascade LSTM, the basic paper, the stances of the replies of these reply tweets towards the source tweet was not considered. So we modeled this verifier itself as a multitask problem, where not only we have to identify whether the source tweet is credible or not, but we also try to classify the stances of the tweets towards the source tweet, stances of the reply tweets towards the source tweet. So in effect, what we are trying to learn is, not only the semantic structure of the text of the source tweet, which needs to be verified, but we are also trying to take the rumor-specific signals from the replies that are being, posted for that particular source tweet. Okay, and on the right, if you see that this is how the two modules are connected in the final model MTLTS. So this is a shared layer. This bird tweet is a shared layer, and you can see that the verified predictions actually are going inside the summarizer, which takes the verified predictions along with its own different techniques to finally decide upon the summary membership of a particular tweet. Okay, so I won't go into too much details about this. So effectively, I would just like to highlight one thing is that a summarunner in essence is a document summarizer. But what we are trying to do, we are basically trying to summarize a bunch of tweets. So we propose a novel method on how to effectively model summarunner to handle such a scenario where there are a bunch of tweets that need to be summarized. So we mentioned, we have a notion of local documents, which is DK. So first, we try to figure out what is the summary membership of a particular tweet with respect to a local context, which is limited by this document DK. And then we try to include that tweet across lots of documents that we make synthetically. And then we try to basically approximate the summary probability of that tweet with respect to several dimensions. So if you see here, this HIK is basically the tweet representation. Then SumIK is basically the summary which has already been formed. Okay, DK is basically the document representation, and verify probability is basically the probability that is given by the verifier, which is working at the lower layer. So the probability of whether a particular tweet, that is PI with respect to DK, the probability of a tweet SI, whether it can be included in the summary of this particular document DK, is actually decided by a lot of factors. And finally, we get the overall probability of this particular tweet SI, which is the source tweet. Okay. So finally, summary in the summary generation, we basically try to optimize this function. So kappa is a threshold. I mean, not a threshold, but it's basically a parameter which is multiplied with the summary probability. So what we are effectively trying to do, we try to understand like how much weightage we want to give to the probability that is generated by the summarizer versus how much weightage we want to give to the probability given by the verifier. So effectively, what will happen if we set kappa equal to 0, then we are giving the entire weightage to the verifier probability. That means we are trying to get a summary which will be, which will be verified to the maximum best possible. And if we try to make kappa equal to 0, kappa equal to 1, then what will happen is we are trying to get a content-rich summary instead of a verified summary. So the results will show what we are trying to do here. So, and this is the dataset that we run our experiments upon. There is a standard dataset FEMI. And for the ground truth summaries are obtained by the authors of the very sound paper. Okay, so there is the qualitative comparison of summaries which are generated by various methods. So we can see that for kappa equal to 1 as expected, if we give the entire weightage to only content richness, then you can see that the Rouge F1 scores are kind of better on an average. So here, yes, so on an average, we can see that when we set kappa equal to 1, then the Rouge 1 F1 scores are going up, and we set kappa equal to 0, that means we are giving all the weightage to the verifier. Then the verified ratio. So this verified ratio is the metric that we use in order to understand whether the summary, what proportion of the summary tweets are actually verified. So that is the verified ratio, a simple metric that we use in order to understand whether the summaries are trustworthy enough or not. Okay, so yeah, these are some observations. We achieve the best verified ratio of summary tweets for kappa equal to 0 and best Rouge 1 for kappa equal to 1. Then, yeah, these are some standard results which we can see that we outperform Verisum with 21 to 35% gains in the verified ratio, which is the important thing that we want to optimize. And finally, in terms of Rouge 1 F1 scores also, we achieve state-of-the-art results. Moving on. So now we wanted to understand like what is the content of the summaries. Okay, the summaries have been generated, and when we are seeing the tables, we see that the scores are good. But now we wanted to analyze the content. So for this, first we identified 4 different classes which are relevant to these FEMI events. So it is victims and casualties, police investigation, other event-specific updates, and personal opinions. And then we make use of a weekly supervised approach to classify each source tweet to one of the 4 classes. So this we do by a CAT-E classifier, which was proposed in WWW 2020, which basically works with respect to the keywords, and it's an unsupervised way to classify the tweets into these classes. And this is the distribution that we get. So what we are observing here is that a majority of the tweets are basically just public opinions. So this, created a doubt in our mind that whether, and you can also see that majority of the opinions are basically verified. So the doubt that we had is that, are we getting better scores in the verified ratio metric just because our summaries are mainly containing these public opinions? Then anyway, if the verified ratio scores are good, but even if, but the summaries won't be actionable anymore, because public opinions, what will we do with that? We need information about the victims, about the investigation that is going on. So these kind of content should be captured in our summaries. So yeah, so for that, what we do is we generate the summaries for different values of kappa, and then we try to figure out that, okay, what percentage of the tweets are of a certain kind. So the value, how to read this value here is that, these are 4 different places. So this value 26.3 means that in the summary that is generated for the Charlie Hebdo shootings, in that summary, 26.3% of the summary tweets are actually related to victims who are affected. Here, for the investigation for Charlie Hebdo shootings, the summary that has been generated, 58% of the summary tweets are actually related to investigation. So this is how we read it. So what we observe overall is that only around 15% of the summary tweets contain opinions. So we were relaxed that, okay, now it's not the case that the summaries which are getting generated, those are only containing the public opinions and nothing else, and that's why we are getting a high verified ratio score. So we are actually generating summaries which are trustworthy as well as they are actionable, because they contain important information about the other 3 classes. So finally, we did one more analysis, is that so this the FEMI dataset has 2 different versions. So in the original version, we have the verified the veracity labels, and there is a later version which also releases the eventual verified the eventual veracity label. Okay, so this using this analysis, what we wanted to see is what kind of tweets actually change their veracity over time. Okay, so yes, and what we are seeing from this table is that many tweets originally which were ranked unverified, they eventually become verified over time, because and the jump is mainly pronounced in the investigation related class, because many of the police investigation related details are not released earlier, so they get released over time. Okay, so accordingly, we see that for the same set of summary tweets, the eventual verified ratio of of the same summary increases over time. So this is what we see, and this is not only related to police investigation; it is related to all the classes, but the police investigation related class is more pronounced. So yes, so to summarize, we present MTLTS, the first end-to-end solution for the task of trustworthy summarization from disaster-related tweets. And different from existing disaster-specific summarizers, our summarizer is basically a supervised one, and it is generally can be applied to many other domains, not only to disaster. And we present a novel way to leverage a document summarization technique for summarizing social media posts. The details can be found in the paper. And when experimenting on the FEMI dataset, we obviously get good scores. So yes, with this, I would like to end my presentation. Get in touch with me if you would like to know more about the paper, and definitely give a read of the paper, and let us know your comments or suggestions. Thank you.
Yeah, so it's a very informative talk. I just wanted to know that can this work be extended to find out cyberbullying? For example, the amount of toxicity that goes in Twitter, on various events, people troll and counter troll. So will your work be able to handle that and probably filter out or black out those comments which are like pretty much offensive. And my second question is that like the events that you have mentioned, say most of them are foreign events. Can it be done for Indian events? Because there are issues with our country as well. So I hope I'm clear with my questions.
Yes.
Thank you.
Thank you for your questions. And I would like to answer the second question first. So absolutely yes, it can be applied to any other, not only any other domain, but any other unseen event. It does not have to be from Europe or from any other particular location. And why exactly we can do that and the other unsupervised summarizers can't do that is because they are heavily dependent upon optimizing the amount, optimizing very specific keywords which are related to those events. But we do not work with the keywords. We are actually getting the semantic content of the tweet. Along with that, we are also trying to figure out what are the signals that are coming from the replies. So this kind of model is actually generic and it can be applied to any unseen event. So that we have already experimented also, and there are some analysis results in our paper, so details can be found. And to answer your first question on cyberbullying, definitely yes, because in cyberbullying also, but given a particular tweet, we are actually looking at the replies and all those tweets which are basically citing that particular tweet. So we are working with the stances, but if we have some labeled data set which can give us this, this direction, like whether the source tweet is actually of bullying nature or not, then we can definitely learn those signals using this cascade LSTM structure, and we can address the problem of cyberbullying.
Any other questions?
Thank you. And our final presentation, Sandeep Juneja from TIFR will present on work that was presented at NeurIPS 2021.
This is the latest one. That's okay. So there's no mic. There's no mic. Yeah. This should be fine, right?
Well, thank you for inviting me for this talk. Very happy to be here. This is going to be a fair amount of mathematics. So if you're looking for a nap, I'll try to help you. This is, optimal best harm identification. So for those of you who are familiar with bandits, this is on bandit problems. For mean and tail risk measures, this is joint work with my student Shubhadra Agrawal at TIFR, but she would have presented this, but she's in Georgia Tech right now doing a postdoc. And Wouter Kulen, who's in CWI. This appeared in NeurIPS 2021, and part of it, which I'll also include, appeared in ALT 2020. Okay, so this is about bandits. Most of you kind of know about bandits. Is that fair to assume? Sequential learning, basically.
Maybe you can give us a summary of.
Sure, that's a great thing. Yeah. Well, it's not so hard, and maybe this picture will explain this. Well, this picture is just what a multi-arm bandit looks like, according to me, because this bandit has everything I consider important: my cell phone, my coffee, and lower bounds. But let me just, if I can move this, which I cannot. Okay, so this picture kind of does the job, So you're given 3 coins, you don't know their heads probability. If a coin was to come up heads, you'll win a reward, say 1 rupee. If the coin comes out tails, you don't win a reward, you get 0. So you have 3 coins. Now, one multi-arm bandit problem very popular in literature is regret minimization. You want to keep on flipping these coins every time you get a reward. You do this very large number of times, and you want to maximize the expected reward you get. So that's a classical regret minimization problem. There's another problem, and that's what I'll talk about today, and that's finding the coin which has the highest reward on average, expected reward. In this case, finding the coin which has 80% probability of success. So that maximizes your expected reward. But you want to do it as quickly as possible. That's the game. And the guarantees, what do you give? Well, somebody told me that I'm willing to live with some error because it's all random. There's always a tiny chance that something strange happens. So someone's told me that, okay, you're allowed error of delta, which is say 1%. So that's pre-given to you. So you're allowed error of 1%. Now with 99% probability, find the arm which has the largest expected reward as quickly as possible. So is this clear? The only thing is, in this particular work, we don't talk about finding the expected reward, but other performance measures like tail risk, right? Which one has higher chance of seeing large losses? Let's say let me just give you some examples as I get to them. So sequentially generate samples from number of arms to find the best arm quickly and reliably. Best arm may correspond to largest mean or smallest C-bar, conditional value at risk, or value at risk. So these are words in the world of finance. People want to say, okay, I have this portfolio of investments. Give me one number which tells me what my risk is. So that number turns out, a number which became popular was value at risk. Amount of money you will lose more than that only 5% of times. So that's value at risk at 95%, or you'll use less than that 98% of times. So that one number, that quantile of the probability distributions, that's value at risk. And expected loss given that you exceed the quantile, that's conditional value at risk. These are very popular measures, particularly in finance, but in many other areas of risk measurement. Basically, they capture tail risk. I won't talk too much about tail risk. Whatever I say has a nice kind of extension to the tail risk. Okay, so some applications to keep in mind. You're given 4 vaccines. You want to see which one to give to patients, right? Which one is the most effective? So this is how this bandit theory started. It was actually for medical experiments, because you want to give the optimal drug to patients, as many patients as possible. Suboptimal drugs have consequences. So that's why you want to minimize those. So which one to give to patients? Worried just not about the mean performance, but also rare adverse reactions. So tail risk also becomes important. If on an average one vaccine is better, but it can have severe adverse reaction 5% times, that's also worrisome. So you want to pick a vaccine which does a good job of this trade-off. Returns from investment in hedge funds. Hedge funds, when you invest in them, so the thing about bandits is this: I pull an arm. That means, so let me just be very clear. I showed you the example of 3 coins. Basically, bandit means I'm given some finite number of probability distributions. I don't know those probability distributions. I sequentially sample from them. I want to find out which probability distribution has the largest mean as quickly as possible. Right? So sampling from a distribution I'm calling as pulling an arm. This goes back to the fact that when the name came about, they thought of the slot machine. Generating a sample was pulling an arm from a slot machine. These slot machines were called bandits. So then there were multiple. So I see the reward from the financial portfolio, but I also see the reward from financial portfolios which I did not invest in. So I get full information. But in bandits, when I pull somebody. Getting exhausted by
No, it's okay.